Okay, we are back with the second in this series, reviewing the introductions to quantum physics. So last time we did a long discussion about the foundations of the Schrödinger equation, and how that equation sort of represents a lot of the basic ideas and interactions in quantum physics. So now something we're going to be talking about is, I'm sure, what was on a lot of people's minds at the end of the last video, which is, well, we have this long, complicated equation. How are we actually going to solve it? And as anyone who has taken any sort of differential equations class, the method will be all too familiar. So just to rewrite it in all of its glory, we have our Schrödinger equation that we're trying to solve, negative h bar over 2m. And we're going to be assuming just in one dimension for now, but you can generalize this. And note that this wave function is a function of position and time. This can be of x, y, z, or whatever. I'm just leaving it this way for now. So now we have I h bar and then the time derivative. All right, so how do we solve this? If I just handed you this equation and said solve for psi, the wave function, that's a tricky thing. However, we have a handy tool here, and that is the fact that v of x is time independent. The potential energy, this potential that this wave function is in, is independent of time. So it's constant. Now there are time dependent potentials. I've seen them before, but I can't remember, a lot about them. Maybe that will be in the future review. I'm sure they are very complicated though. A lot of cases throughout many of the first years of quantum physics are all time independent potentials. Whether that's realistic or not, who knows, but we'll get into it anyway. So this enables us to do a handy trick. As I said, if anybody took a differential equations class, this will be extremely familiar. So now I'm going to rewrite this. I guess this should be uppercase. This should be lowercase, but we're going to do a separation of variables. So we're going to assume that this function is actually two separable functions, one of position and one of time. And we're just going to multiply them together. And this is a really common technique for solving these PDEs at a simple level, I guess. And it's a really powerful tool as well. So now that we have this separated out, we can see something important. We can see that this equation can be separated into time and position components. Because we have this up here, now let's look at each of these terms. So this becomes simply v of x, psi of x, and of t. That's pretty straightforward, just multiplication. This term, this partial derivative, becomes negative h bar squared. Did I forget the squared? Yes, I did. Negative h bar squared over 2m. Then we can take our f of t out because it's just a constant being multiplied here because the derivative is with respect to x. And, oopsies, this should not be f of t, but... And then we have our position, the x squared. And then over here, this term becomes I h bar. And then we can take our position term out because, once again, this derivative, it's just with respect to time. So it doesn't actually matter, what this is for the position. I should be writing d instead of the partial sign because these are now all functions of one variable. So just pretend that these are all d's instead of partials. So now that we have that all written out, what we can do is we can divide both sides by this function. So if we say, okay, we're dividing both sides by this function, which is, so we're dividing by xt, basically, what do we get? Well, we see right away that in the first term, this t will cancel, and we'll be left with a 1 over psi of x. So we'll have negative h bar squared to m 1 over psi of x, and then we'll still have our partial here squared of x, and then we will have our plus, and here the v of x gets canceled out entirely, right? And we can see we have just now v of x. And then on the other side, we can see the position gets canceled out, so we'll just have I h bar over the time function, and then the derivative. Here I'm doing it correctly, the derivative of this time function with respect to time. And we can rewrite this in a handy way. If I just extract this part out, if we take this out, we'll have 1 over the position, and then we'll have negative h bar squared over 2m. I'm going to write it correctly this time, the derivative of psi of x with respect to x plus v of x psi of x, right? Because we took 1 over, so if you distribute it, it'll cancel out. This is equal to the same thing as above, I h bar over the time, and then we have our derivative. So what we have successfully done here is made these two functions independent of each other, in the sense that this is now independent of time. You can see there's no time variables over here, and this is independent of position. There's no position variables over there. And since they must equal each other, we can say, okay, they must equal some constant, c. So both of these must always equal something, even if you vary, you know, whatever time or whatever position, they will always equal each other. And we can set that equal to some constant, right? Because they have to equal something. This is just some constant number, I should say. This is some, you know, real or complex number. In this case, I can tell you it's going to be real, but that's for reasons we'll get to later. And rather than call it C, let's give it a handy name. We'll call it E. And you might recognize this quickly as being the energy, and that's why we're calling it E, but we'll see more later. So now that we have both of these equations equal to E, we can now solve them. This one looks a little tricky. So let's solve the easier looking one first, the time one. So we have the little sheet. We have E equals I h bar over time, and then we have I'm really tilting d dt. All right, well, let's just solve this as we do for differential equations, get this all by itself. So we'll have d of the function dt equals e over I h bar times this function. Now we can just rewrite this. This is the same as negative I e over h bar, because if we multiply this by I over I, which is 1, we get I over negative 1 and negative I. So this is just equivalent. This is just the standard way of writing it. So now we have a very simple equation to solve. We have the derivative. Here I'm just going to write it in a different notation to make it even clearer, I think, for those of you who have less diffie-q experience. Negative I, e over h bar. So what would solve this equation? Well, you could, obviously just solve it normally, integrate both sides, get your solution, right? But this looks pretty easy to just say, oh, well, I recognize this. The derivative of a function equals a constant times the same function. And well, that's, everybody's favorite function, e to the c, right? The derivative of e to the c, ddc, we'll make as a function of time, d dt equals c e to the t c. Oh my god, I can't. Right? That's just the rule about the exponential functions, because you have the, yeah, that's just, basic calculus right there. So we can see right away that our time function is e to this times t. So we have e to the negative I e t over h bar. And that, right away, is our solution. However, it should be said that this is a differential equation and we need a starting point. So we have our time function is equal to our initial condition. So whatever our initial condition is just our some constant, right? Because this is just a function of time. So whatever e of 0 is here, we can say that this is the initial condition. E of 0, as we can see, and using this equation, would be 1. So moving on, we have, I'll just circle this as this is, we just solved it. We solved the Schrodinger equation for time. This is the solution. So now we have what's called the time-independent Schrodinger equation up above, which is basically this section right here. This is what's known as the time-independent Schrodinger equation. And now we want to solve it. So the way we do that is first, of course, we move our wave function over, right? We had 1 over the wave function, so we'll have negative h bar squared over 2m. The derivative, the second derivative, sorry, I keep saying derivative, second derivative with respect to x, plus the potential times the position. And then we moved our wave function over, right? That was being 1 over here. And this is the Schrodinger, the time-independent Schrodinger equation, right? Nothing depends on time. And we can see how it also renders it an eigenvalue problem. So we can see that these two terms make up what's called the Hamiltonian, and E is the eigenvalue, a single number that represents this Hamiltonian's eigenvalue, because, right, if we have, h hat, this is our fundamental eigenvalue problem. But we'll get into that a lot later. So for now, what we're going to be looking at is, well, how do we solve this one? This is a tough one to solve. And right now we're going to be saying, okay, well, a closed form solution to this general equation is pretty tough. So let's look at for specific potentials, right? Solving for a general potential is, solving in any meaningful way for a general potential is not as useful right now. So let's look for specific potentials. How do we do this for a general potential? I don't know, that's too hard, right? So let's make it easy. Let's say v of x is known, and then we can solve for things. So the first thing we're going to do before that is make one note. And that is something that this was the hardest thing for me to grasp when I started quantum physics. It is now the easiest thing because it's so basic in quantum computation. And so for those of you who come from quantum computers, this is going to be like, why are you even saying this? But for those of you from a classical physics background or no physics background, this was literally like the hardest thing for me to grasp. I'm not 100% serious here. I had to, when I was, we had cheat sheets for tests. And we were allowed like 1 page of notes, basically. We called it a cheat sheet. This was basically where I wrote time and time again just to remember it. I didn't get it. It took me a while to get it. You can see that I was not very good at physics. So our big wave function, which I'm going to represent here, this is our wave function. Here, this can be, we can just say this is a function of x, but we can also say it's a function of x in time. It doesn't really matter here. This is a linear combination, sum meaning linear, of a variety. In this case, we can write this as infinity of wave functions. So this is trivial in quantum computation. Now this is a finite Hilbert space we're dealing with in quantum computation, so it's not infinite, where we have, our wave function would be, this could be 1/2 0 plus half 1, right? So this is obvious. This is just the sum is, this is our wave function, and where c of n would equal 1 over square root of 2. Now that's straightforward, but keep in mind in the continuous case where we're not dealing with these discrete states and we're not dealing with a finite number of these discrete states, we have an infinite spectrum here. And so we can see that the c of n squared is the probability that this big wave function equals this wave function n. And that's the same thing over here, right? The probability that this will, upon measurement, equal 0 is 1 over square root of 2 squared, which is 1/2. And we can also see that this can be revealed in, if we look at if you solve the integral out for this negative infinity to infinity and star dx, we'll get, you can write this in terms of the equations, you'll do it out, you'll get this, I'm skipping some intermediate steps here, and then this is the, basically this function here is 0 if n is not equal to m, and 1 if n equals m. The Kronecker function is what it's called, or Kronecker delta function or something like that. And so this will equal c of n, which is exactly what we would expect, right? If we're used to quantum computation and we have the wave function right above 1 over square root of 2. Here, I'm going to change this a little. I'm going to make it 1 over, can I do this off the top of my head? Okay, pretend this is normalized. 1 over square root of 3, 0 plus 1 over, that'd be 1/3, 2/3, so I need square root of 2/3. Okay, yeah, just pretend, I think this is normalized, but just pretend it is in case it's not. We can see that this is a continuous sort of version of saying we want the inner product of, let's say, 0 and our wave function, where this is our wave function. We can see this is going to cancel out because they're orthogonal, and we're just going to be left with 1 over square root of 3. And this is all it's saying, sort of drawing analogies to the quantum computation sense. All right, now that we have all of that out of the way, let's get into actually talking about some of these potentials that we could solve for. Interestingly, a lot of texts start with the infinite square well as the sort of basic potential. I'm sort of debating right now whether I want to start with that, or the simplest to me seems like the free particle, which means there's no potential. But I guess we can just do the square well, since I didn't prepare as many notes on the free particle. And for some reason, yeah, I guess we can just do the infinite square well first. And that's what's ahead of this title anyway. So the infinite square well, this potential is very straightforward. We have, oh, sorry, before we get to the infinite square well, the one thing I want to say is that when we have our function, right, x of t, we now know that we solve for t, right? So we have e to the negative I, e t over h bar. You'll notice in a lot of cases, right, if we want the, I don't know, probability or the expectation value of some operator, right, we'll do this negative infinity, infinity, right? If we have the expectation value of some operator we care about, we'll just do x, right? The position operator that we care about for this wave function, you'll notice that we'll have psi star x psi, x will get brought out here, and we'll have psi star psi. In any case where we have this sort of interaction, right, where we have this inner product of these operators, this will always cancel out because we have the complex conjugate. So we'll have e to the I, right? The complex conjugate is removing the negative sign, e to I t over h bar, e to the negative I t e over h bar equals 1. So these will always sort of cancel out basically in these similar sort of situations. That's just something to note. That's a really handy tool. Is a lot of times we'll be like, oh, I have to deal with this exponential, but nope, it'll usually cancel out in some way, shape, or form. Not always, and we'll get to those cases eventually. So now let's talk about the infinite square well. The infinite square well is the case where we have a potential v of x that is equal to 0 in the case that we have it within some bounds. So we have, just deciding what variable to use here. Everyone uses different variables. We'll do negative, we'll just do 0. No, probably 0 is less than x is less than L, right? And otherwise it's infinity else. So what does this look like, right? If we're visualizing x here, that's a bad line. Our function x, and this is v of x, right? This is, we'll say this is 0, this is -1. I know the axis is off. I'm just writing it. This would be what it would like. This would go up. This would be here. This is L. This would go up to infinity. So in this little region, the potential is 0. Outside of it, it's infinity. So what does that mean? That means a particle cannot exist outside of here. The wave function where x is greater than L is not allowed. You cannot have the particle outside of this box because it's infinite. That's just, how these infinities work. So what does that mean? Well, that means that we only really have to care about this wave function, our wave function, which is time independent. The potential is time independent, so we're just going to be ignoring time for now. We'll bring it in later. This wave function we only really care about from 0 to L, because outside of it, the particle won't be there. This particle in a box, right? This wave function is representing some particle in this box, which has infinite walls. The particle is not going to be outside the box because they're infinitely tall walls. So now let's solve for this. Well, how do we go about doing that? Well, the first thing we can write is we can say, okay, well, inside this box, which is all we care about, right? Because it can't be outside the box, we have our equation, negative h bar squared over 2m. We have our second derivative of this function, x squared, and then our potential is 0. So we just have e. So that's all our function is, right? That's the problem we're trying to solve. And if we solve this, we can get the wave function. So now, well, we can, as we do with partial differential or differential equations, this isn't a partial differential equation, this is a second order ordinary differential equation. If my diffie-q terminology is correct, we want it to be by itself over here. It's often a handy thing to have. So we'll have negative e, 2em over h bar squared, right? Just multiplying that out. So what we can do, and what's commonly done, is substitute just an equation here for it. We don't have to do that, but it's really common. It's just to say that this is equal to k squared, just to reduce the amount of numbers we have to write. So k, of course, would then, sorry, this is negative k squared. K, of course, would then be the square root of 2em over h bar. So if we just rewrite it just to be nicer, we have the derivative here. I'm just going to be writing this in a simpler format, equals negative k squared. You'll notice something right away. Hey, wait a minute, this looks really similar to the time equation, and that's because 99% of the time it seems like it is the exponential solution. So let's just take a guess, right? Okay, we have is e to the kx maybe, right? I don't know, negative kx. Take it down, we would have e to the negative kx, negative k, and then we would have, take it down again, e to the negative kx, k squared this time, because the negatives would cancel. So there's a little something else going on here, right? Perhaps we should add in something else. we can represent these exponentials, right, in a similar way to sine and cosine, right? There's that relationship when you have the imaginary number that these exponentials are equal to each other. So that seems similar, but maybe we're barking up the wrong tree. So let's try something else. Let's try sine and cosine, right? Because we thought it was exponential. Sine and cosine are intimately related in this imaginary sense. So let's try it. We know that if our equation is some combination, a sine of something times x, bx plus c cosine dx, that the partial derivative, the first partial, right, is we can separate them because they're added. So the first partial would be a b sine, sorry, I gotta do this right, cosine of bx, and then this would be negative ab squared sine of bx, right? This would be the second derivative. This would be negative c d cosine, I don't know, I should capitalize this, cosine of dx, negative c d squared cosine dx. So that would be the equation. So what do we want? We have a negative k squared out front. If we set a and c equal to 1, we have, just for now, we have negative k squared equals negative b squared sine of bx minus d squared cosine of dx. Well, what do you know? K equals b and d, we get our answer. Oh, this should be our function. Right, so we have our answer here. We know that it's going to be of the form, our original equation is going to be of the form sine of kx plus, now we still have our a and c here, cosine of dx. Sorry, this is k now. We established that this is k. And the reason I put them back in is because now we have some important boundary conditions. We solved for the inner part, but now we know that we have, right, the walls of the cage that we put our particle in. This has to equal 0, and this has to equal 0, because it's 0 at that line, and anything past the infinite square well it can't be there. So it has to be 0. So I put restrictions, right, on this function. So we know cosine of 0 is equal to 1. So c must equal 0 for this to be true. So now we have psi of x, or psi of 0 equals a sine kx, which doesn't tell us a lot because sine of 0 is equal to 0. So now let's go to the other boundary condition. We have of L equals 0. So we have a sine kx equals, sorry, this is KL now, KL equals 0. So now we can say, okay, this is true when KL is equal to, you know, n pi, right? Because sine is 0 every pi at 0, pi, 2 pi, 3 pi, 4 pi, where n is some, you know, natural number here. So then we can say, okay, divide it out, and we will get the specific kn equals n pi over L. And that's a specific, right? Where n, we're specifying is one of these values, and that will equal 0. So a here is just this normalization that we're leaving in, right? Because if we now have established that we have our wave function, we solved it, right? We did it. Congratulations. A sine, here I'm going to be writing kn times x, or a sine n pi L times x. This is our solution, but we have to know that this, the integral of this is equal to 1. which does not seem trivially true. If the integral from negative infinity to infinity of sine of n pi x over L, I mean, that doesn't seem trivially true, at least to me. So what we need to do now is normalize this to get our final solution. And the way, remember, we did a normalization example next time is by simply saying from negative infinity to infinity, we need this wave function to be equal to 1. But let's notice something outside of 0 to L, it's 0. So we can restrict this down and we can say, okay, we have a squared because I guess a could be complex. So I'll do a that way. And then we have our, right, the conjugate. This is all real, so we don't have to worry about that. So we have sine squared of n pi over L times x dx. So we can take, of course, our a squared out, and we can now do a handy trick. Those of you familiar with trig will know that your identities. I, of course, do not have them memorized, but sine squared of x is equal to 1 minus cosine of 2x, which is 1/2 actually, 1/2 minus cosine of 2x. So that's just an identity. You could probably prove that or derive it or something, but we would just know that you can look it up, and that's the identity we're going to be using. So we can say, hey, wait a minute. We now have our handy little substitution. We have sine squared. I don't know what the integral of sine squared is. So let's substitute this. We have 1/2 1 minus cosine of 2n pi. It's an n pi over Lx. Oh, got a little close to the edge there. Let's write that's another parenthesis. All right, so now we can take our a squared over n, it's over 2 out, and we still have our integral from 0 to L. We have 1 minus cosine of 2 pi n over Lx. Now, of course, we can separate this out. We have the, dropping this for now, I'm just going to be zooming in on here. We have the integral from 0 to L of 1 minus the integral of 0 to L of this cosine thing. So the integral from 0 to L of 1 is x, right, assuming dx, 0 to 1, 0 to L, we have L, of course. And then cosine, we have sine, right, is the integral sine of 2 pi n over Lx. However, we have to, if we take the derivative of this, we get 2 pi n over L. So we have L over 2 pi n in front. And then we want to evaluate this from 0 to L, which leaves us with, at 0, this is all 0. At L, we have L over 2 pi n sine of 2 pi n over L squared. 2 pi n, right? Because the L will cancel. And of course, we know that 2 pi n is 0, as we already established, right? Because we already know pi n is 0, and 2 pi n still keeps it an integer. So this is going to be 0. So we're left with reintroducing our normalization constant, a squared over 2. We're left with L, right? Because this L from the integral of 1 is still there. This equals 0. So we are left with a squared equals, 0. Why did I say 0? I was like, that doesn't make sense. It equals 1, right? Because this is our normalization. This must equal 1. So we have a squared equals, divide by L, multiply by 2, 2 over L. A equals the square root of 2 over L. And now we have our normalization constant, which allows us to write the true and normalized solution to the infinite square well potential Schrodinger wave equation I'm reintroducing time here. So we have our time, e to the negative I e t over h bar. We already solved this. This is just generally true. Times our normalization constant, 2 over L times sine of n pi x over L. There we go. That is our Schrodinger solution. Of course, this is bounded by, this is 0 is less than x less than L. Otherwise, it's 0, right? Outside of that. This has a lot of handy properties, this solution. Specifically, for the increasing wave functions, right? So we said above that our big wave function is a sum of little wave functions. We can see that these little wave functions are obviously going to be defined by this n. So for n equals 1, 2, 3, this big wave function is a superposition of those wave functions. Now, it could be entirely in one state, but it can be represented in this format. There's a number of handy things here, and that is that for n going up, these alternate between even and odd functions. So what is an even function? What is an odd function? Even functions and odd functions are defined by the following identity. Even functions have, let me make sure, I always get these two messed up, so I'm just double checking. Even functions have f of x equals f of negative x. For example, x squared is an even function. Odd functions have f of negative x equals f negative f of x. So this is x, right? That's the trivial example, would be an odd function. And these have a lot of nice properties that you can work with. So that's a handy property of these solutions. Another handy property is the fact that if you actually plot these, right, so n equals 1, if we do this in our infinite square well, will look like this, right? It's just going to be a sine, part of a sine function, right? Obviously, if this continued, it would be like, a sine function. But what happens at each increasing level is we gain a node. So 2 would look like this, 3 will look like this, 4 would look like that, and so on. And this node, or crossing 0, right? How many times this is 2, this is 1, that's 0, that's 3, 1, 2, 3, etc. Is what the wave function would actually look like. These are also orthogonal to each other, i.e. the integral from negative infinity to infinity of n m is equal to 0, assuming that n and m are not equal to each other. We can also say that this is complete. This is a complete function. So our combination, right, we have our from infinity to n to square root of 2 over L of c of n sine n pi x over L, right, where c of n is our probability of representing, of being in this state, right, of being in this particular example. Of course, we have our time here. I'm just going to write it there. This can equal any, function. Anything you can represent via this. That's a real pain to prove, and I think most of the times we just assume that this is the case. I think you do probably some Taylor expansion or Fourier analysis of this. I have no idea how you'd even prove that, but this is true. You can represent any function using this superpositions. And so that's a lot of handy properties for this infinite square well solution. The most important thing that I want to talk about, though, now that we have the solution, is what does this look like for the energies, right? Because, okay, well, we have our wave function, but now what does the energy look like? So if I scroll way back up, somewhere in here, we wrote the Schrodinger equation for the system. Should be after this. Yeah, here we go. We have this negative h bar squared over 2m equals e thing right here, right? So what we can see from this is that, I would just mark it right here. We can see that when we wrote k squared, we have k squared, right, is equal to 2em over h bar squared, which means if we solve for e, we have k squared h bar squared over 2m. Of course, we know I'm going to now move this down to the bottom. So we're solving for our energy, right? We know it's equal to k squared h bar squared over 2m. We now know that k squared is a function of kn, right? That's something we have now established as k is kn for our solutions. And we know that kn is n pi over L, so we have our energy solution. Energy equals h bar squared n squared pi squared over 2ml squared. So that's our energy for each of the n wave functions, sub wave functions. I don't know what the proper terminology is here, right? Where we have the sum. So each of these is defined by this n, which increases quadratically, right? Because h bar, m, l, pi are all constants. It's only a function of n, really. We can see that e scales, if we're using some terminology here, quadratically with n, because these are all just constants. Of course, h bar squared is a very small constant. But that's not the important thing, is how it scales. The important thing is that the energy levels are discrete. For each wave function, there's an associated discrete numeric value of energy. You can see it's real from, since everything going into is real, we can see the energy is of course real. And this is why we were just talking, when we talk about quantum mechanics, we're saying the energies are quantized. There are energy levels that this can exist in. It cannot exist. You can't measure, for example, any energy. So if we have an energy equals 3 or something, and that doesn't align with the constants, you can't, it's not allowed. It can only be measured right at these discrete energy levels. And that's a very important note that will come up in a lot of ways in the future, is that this concept of quantization of energy levels that explains a lot of things, atomic spectra, emission spectra, all of these things we'll get to later will be related to how these quantized energy levels exist. I think that's going to be everything for now. Next time, I guess we will get to probably the most popular, and that is the simple harmonic oscillator as another potential. This first part is just dealing with a lot of potentials. After that, we'll probably do the free potential, which is v of x equals 0, free particle, and then maybe finite square well, finite square well. And then after that, that should all be probably one video. Harmonic oscillator. Let's see what's next. There's a lot about the generalized statistical interpretations. I already talked about the eigenvalues, vectors, and operators. We don't need that. Oh yeah, wow, this goes straight into the hydrogen atom. Okay, yeah, so we'll probably do we did finite square well. We'll do simple harmonic oscillator, finite square well, free potential, and then maybe, what's after that? Oh, probably the double well, quantum teleportation. Not teleportation, tunneling is what I was going to say, tunneling through these finite wells. And yeah, and then we'll probably get to the hydrogen atom, and then talk about, let's see, that's observables. Then we'll probably talk more about the Heisenberg uncertainty principle, and then we'll get into hydrogen, spin. Oh wow, there's a lot of stuff. Identical particles, yeah. So that's just a brief glimpse of the future. But that's it for now.